Hello again. Today our topic is the periodic table, and our objective is this. The periodic table is arranged in a way that patterns show up with the elements. And so the patterns can be both the physical properties of the elements and also how they behave chemically. How do they react? And so what we're going to be doing is you're going to need a periodic table for this. And so if you don't have one, go Google periodic table black and white and print something like this out. Because we're going to manipulate it. We're going to write on it, we're going to color it, and try and make some sense out of it. And by the end of this, I want you to have an appreciation for how the periodic table is arranged and organized, and just to see that there's an order in the universe for how matter is structured. And so let's take a look at that. There it is. I'm sure you probably already have one in your pocket periodic table. We're not going to memorize it, but we're going to appreciate it. Because right now, if you look at it, maybe it's just like a jumbled mess. It doesn't make any sense, but it will. Quick shout out to Dmitry Mendeleev, who gets credit for being one of the first to start organizing elements in a way that the patterns show up. So this is what he came up with. And what's cool is, one, he came really close to what we have today, and two, he saw that he was missing some elements because they hadn't discovered them all. But he knew that something, so he left placeholders here. Something was missing because it was messing up his pattern. Pretty cool. So here we go. We got some notes. The essential questions. What is the periodic law? And then what are some patterns that show up on the table? We're going to get into both of those things. The first thing is the periodic law. When elements are arranged in order on the periodic table with their atomic number, patterns show up. So take a look over here. Hydrogen, atomic number 1, helium 2, lithium 3, 4, 5, 6, and so forth. Mendeleev didn't know atomic numbers, so he did it by atomic mass, and he still got the same patterns showing up. So that's the thing number 1. And you can hit pause on this. By the way, you don't need to write, don't try and copy this row of the periodic table down. We'll talk about that momentarily. But for right now, on your periodic table, we're going to start writing on it. So remember, hopefully you were in class when we did this. We arranged, we figured out how many valence electrons different atoms have. Remember, the valence electron is the number of electrons in the most outside shell. And we found that everything in that first column, which we call a family on a periodic table, this first group, family, has 1 valence electrons. Everything in this one has 2. Everyone in this column, 3, 4, 5, and so forth. I want you to write that in. Make sure you line up the numbers with the family. Why is it called the family? Because everything in that column behaves very similarly, like people in a family might sometimes. Over here, 8 valence electrons. Remember, the octet rule says most atoms want to have 8 valence electrons. That's how they fill their shell. And so these guys over here, they are happy. They got full shells, and every other element on the periodic table wants to be just like them. And what they're going to do is they're either going to give away electrons or bring in electrons to fill out their shell, gain them. And so let's take a look at how this works. In group 1 here, family 1, everything's got 1 valence electron. So what is it easier to do? To gain 7 more to fill out your shell, or lose that 1 and then the shell below that is full already? They're going to lose the 1 electron. And so let's take lithium, for example. If it has 3 protons, 3 positive charges, and 3 electrons, 3 negatives, and it loses 1 valence electron, now it's got 3 positives and 2 negatives, it leaves it with a +1 charge. The whole column has got a +1 charge. Beryllium, 4 electrons, 4 protons, it gives away 2 electrons, it leaves it with a 2+ charge. Whole column. Write these numbers in. 3+ charge. And then working backwards, for chlorine, for example, it's got 7 valence electrons. Is it going to gain 1 or get rid of 7? It's going to gain 1. And we're going to talk about why in a little bit. But if it's neutral and then we give it 1 negative charge, now it's got a negative charge, or a -1 charge. If we give oxygen 2 electrons to get it to 8, now it's got a -2 charge. Write that in. It's going to help you out a lot. Moving along. First, now get the colors. Whatever color you have is fine. We're going to color in that family that has 8 valence electrons. These guys are happy. They're stable, and they don't really react with anything else. They're already happy, and we call them the noble gases. Make sure you make a legend for yourself. The noble gases. And one of the things that, I don't know if you can read that, but they get heavier as you go down the column, right? Helium is much lighter than these ones down here. And I wish I could show you my favorite English guy doing this demo. I'm going to leave you the links, but it won't play the way I have it set up within this thing. But it's just 1 minute. It's interesting. The next family we're going to color in are these here with the 7 valence electrons, and they become -1 charge when they gain a valence electron. These are called the halogens. They all behave in a similar way. Make sure you make a legend, whatever color you want. Then we've got the alkaline earth metals. They all have a 2+ charge. Color that in. And then finally, we've got the alkali metals. All have +1 charge. And these are my personal favorite, and I'm going to guess maybe yours too if you know anything about them, because they're really reactive. They're really interesting. So color those in. And again, I wanted to show you this video. It won't play. I can't do a video within a video the way I've got this thing set up. So I'm going to leave you the link so you can watch it again. But one of the things that we find when we watch that video is as we go down the column or the family, it gets more and more reactive, more and more explosive. And so that's going to lead us to our next thing. And so of course, here's the next periodic table, next slide going from this one. So we've got 4 things identified. And then I'm going to have you do one more thing that I want you to make a little staircase down here. And if you look at this one, you can shade everything in one color. They have more subgroups here, like metalloids and things like that. But really, this whole side of the periodic table is all metal. That's another pattern. Over here, we've got all nonmetals, and over here we've got all gases. And so we're starting to see those physical properties show up. And so back to, there's one more thing I want you to write down, then we're going to talk about it. With a big arrow, I want you to write ionization energy decreases as you go down. And ionization energy increases as you go across the periodic table. So write that on your periodic table somewhere. I'm going to hit pause if you want to look at that. I'm going to keep on going here. And so ionization energy, here's what it is. It's the energy required to remove an electron from an atom. And so we're going to go across the periodic table here, and we call that a period. And so here's the period I've got. It starts with potassium, and it goes all the way over, okay? And so let's just look at this. I've got potassium here. It's got atomic number 19, which means it's got 19 protons in the nucleus, 19 plus charges, compared to bromine, who's got 35 plus charges. So which one of those has got a bigger attractive positive force? It's the bromine. And so if we're thinking about keeping electrons, negative charges close to us, which one's going to have a bigger pull on the electrons? Bromine. It's got a bigger positive charge. And so it's a lot harder for bromine to lose electrons. That's why it takes more and more energy to get rid of those electrons as you go across this way, because every atom is a little bit bigger and has a little bit more of a positive charge than the one to its left. Okay? And this is why these ones want to gain electrons. They're not giving them away. They can easily gain them because they got a big positive charge. So bromine, chlorine, fluorine, all those will gain that one electron in a hurry. The other one going, so across the ionization energy increases. We just talked about that. Down the family, here's that group of alkali metals, the energy decreases. Why? It's because if you think about lithium, lithium is a small atom. It's got one valence electron, it's that little red dot, but because it's so small, that electron is really close to where the nucleus. And so it's going to be a little bit harder to get rid of that electron because it's closer to the positive charge. If you look at this, here's rubidium, and it's got a 37 plus charge. It's just a bigger atom, a bigger nucleus. Here's its valence electron. They both have just one, but just look at how much is that little red dot. Look at how much farther away that is. Way easier to get rid of that because even though it's got a big positive charge, this electron is so far away, there's not a whole lot holding on to it. Okay? And so it's called ionization energy. And with that, we are going to cut this little instructional video off. You now should have a periodic table that's got a bunch of numbers on it, some arrows. You colored that in. Hopefully you colored in the leftover non-metals over here. And I want you to write a summary down here that explains the periodic law in your own words, and then write some examples of patterns that you see there, whether it's how they react, gases, ionization energy. So as we go down the column, it gets more and more explosive. Watch that video and you're going to see what I mean. Okay, thanks everybody. And if you have any questions about this, leave them on the Google form and we'll get back to you.